Today is our ninth lecture and the topic is clamper circuits. A circuit which adds DC value to an AC waveform without changing its shape, it is called a clamper. A clamper is used to reinsert, re-improve or add DC voltage levels into an AC waveform either in the upward direction or in the downward direction, which has lost its DC by passing through an electronic processing circuits such as amplifiers. Means a clamper circuit is used to reinsert DC voltages into an AC waveforms where required. For example, there is a figure given in this slide. At the input side, there is a weak AC signal with some DC component, and we want strong AC. We want to improve, reshape AC signal, weak AC signal. But the problem of this circuit amplifier is that when it amplify the weak signal, AC signal is amplified, but the DC signal is lost in the input weak AC signal. So at the output of the amplifier, you see the output is strong AC but without DC. It means that DC is lost in the AC signal. So then we use clampers. It means where we use, you can understand it with this figure, that we use these circuits after all those processing electronic circuits where we need DC component, DC levels with the AC signals. So right after the amplifier, we place clamper circuit, and at the input side of the clamper circuit, now there is a strong AC without DC signal, and when we input this AC signal without DC to the clamper circuit, so at the output side you will see after passing through the clamper circuit adds certain required level of DC signal into this AC sinusoidal waveform. So it means the importance of clamper circuit is that it can reinsert, it can re-improve, it can add DC voltage levels in any AC waveform where it is required, or it is the requirement of the design problem. Second important thing, that the clamper circuit is used as a voltage shifter. Means the input waveform of any signal remains unchanged. At the output side, the waveform remains unchanged, but there is a certain level of addition of DC levels in the voltages as shown in the output side, which you will see in the next slides. Dear students, it is also used as a voltage shifter. It's a voltage shifter. It shifts the voltage levels from one cycle to the other cycle. It means at the end you will see at the output side the total voltage remain the same. So these are the clamper circuit. One example I want to share with you. Here I use the volume control in TV. You all have TVs at your home. When you increase this volume in the TV, it is basically adding the DC level through the clamper circuit. So it means this is a very basic circuit which is also used in TVs. When you use the volume button, what happened? Basically, there is an addition in the DC levels. So this addition is through increase in the volume. So this is an example of this clamper circuit. Now the classifications of clampers. A clamper circuit is a circuit that adds a DC level to an AC signal. The positive and negative peaks of the signals can be placed at desired levels using the clamping circuits, as I have already discussed in my previous slide. The DC level gets shifted. A clamper circuit is also called as a level shifter. There is not a wide classification of clampers as like clipper circuits, because clipper circuits classified into many types like positive, negative, biased clippers, biased positive, biased negative clippers. It may be biased or unbiased, but here in clampers the classification is very simple. There are two types of clamper circuits. Negative clampers, very simple, which adds negative DC voltage levels. When we add negative DC voltage levels, means waveform will shift towards or shifted to the downward direction. Second type is positive clampers. It simply adds positive DC voltage. When we add positive DC voltage, means waveform will shift it towards the upward direction, or it shifts to the upward. Now let's see negative clampers. Clamper circuits consist of energy storage elements like capacitors. A simple clamper circuit comprises of a capacitor, a diode, a resistor, and a DC battery if required. But in the circuit given below in figure number 2, we use only a capacitor and a diode. It's a very simple negative clamper circuit for understanding. In negative clampers, we add negative DC voltage. The waveform will be shifted in downward direction. In positive clampers, we add positive DC voltage. The waveform will be shifted in the upward direction. Now further discuss in detail. We are starting with the negative clampers. The circuit for negative clamper is shown as below in figure number 2. If you will observe, you can find a new component in the clamper circuit like a capacitor. While there was no capacitor in clipper circuit, it's the difference between a clipper and a clamper circuit. Now it's a hint that if there is a capacitor connected in the circuit, then it means it's a clamper circuit, or it can be a voltage multiplier. Now it's a clamper circuit as shown in the figure number 2. So we input Vi, which is 10 volt as shown in figure number 1. Vi can be any AC waveform with 0 DC. Here we choose a rectangular waveform as shown in figure number 1 as a Vi we input so that we can understand this clamper operation easily. Now for solving problems, please keep it in your mind. One important tip. Dear students, always start working from that cycle which makes the diode forward biased in the negative clamper circuit. Means there's a question from which half cycle we should start function of this clamper circuit. We always start function from that half cycle which helps the diode to forward bias. It means it's the need that the diode must be forward biased in the first half cycle. As we all know the operation of diode, when we provide positive polarity at the anode side and negative polarity at the cathode side, the diode is in forward biased and acts as a short circuit. So in this case, we first choose positive half cycle for the negative clamper circuit as shown in the figure number 1. In case number 1, we apply V input as a rectangular AC waveform as Vi is equal to 10 volts as shown in figure number 3. In case number 1, we apply conditions for positive half cycle, and these conditions are: if Vi is greater than 0, means V input is greater than 0. Consider in positive half cycle or Vi is greater than 0, then the diode D is in forward bias and act as a short circuit as shown in figure number 1. Now here in figure number 1, when we apply Vi as a rectangular waveform, capacitor start charging in this positive half cycle up to V maximum, up to Vm. So Vm is across a capacitor which is connected in negative clamper in figure number 1. So here in this case we have to find V maximum across the capacitor and V output, the output voltage. So first find output voltage, which is V out Vo. Here V output is equal to 0. Why? Due to both the terminals are short circuited as shown in figure number 1, due to which diode is in forward bias and acts as a short circuit. When diode acts as a short circuit, so V output is equal to 0 in this case number 1. Now we find Vm. The value of Vm by using Kirchhoff's voltage law KVL. The current flowing through the capacitor as shown in figure number 1. Here we mark positive and negative polarities at the plates of the capacitor. Now we are going to apply KVL. According to figure number 1, there is a closed loop as shown in figure number 1. So it's very simple to apply KVL. We have voltages Vi and Vm. So it is minus Vi plus Vm is equal to 0. So Vm is equal to Vi, which is we have already seen in our previous slide, because Vm is charged at maximum value of Vi, and the maximum value of Vi in the rectangular waveform is 10 volt. So Vi is equal to 10 volt, means the capacitor will charge up to Vm, and Vm is equal to 10 volt, means the capacitor will charge at its maximum voltage of 10 volt, which is shown in Vi in rectangular waveform. So Vm is equal to Vi and Vm is equal to 10 volt. Now consider second case. So in this case, now we choose or apply negative half cycle for this negative clamper circuit as shown in figure number 2. In case number 2, we apply rectangular AC waveform as V is equal to minus 10 volt as shown in figure number 3. In this case number 2, we apply conditions, and the condition for this case is in negative half cycle Vi is less than 0. Now Vi is less than 0. The diode D is in reverse bias and acts as an open circuit as shown in figure number 2, because we have already discussed in our previous slides in clippers and in my clampers previous slide that if the polarity is opposite with respect to the anode and cathode of the diode will be forward biased and acts as an open circuit, which is clearly shown in figure number 2. Now when we apply negative half cycle, the polarity of the capacitor will never be changed. It remains the same as in the previous case of the positive half cycle as shown in figure number 2. Means the capacitor is already charged up to Vm P maximum. Now the diode is in reverse bias and acts as an open circuit as shown in figure number 2. So here in this case, no need to find the value of Vm max value across the capacitor, because you have already found the value of Vm in the previous case when positive half cycle is applied to the clapper circuit. Now here we have to find V output. Now there is an important point that if we start with the negative half cycle in case number 1, then it is difficult for us to know that capacitor is charged up to which value of Vm. So then it is difficult to find the value of Vm. That's why we always start with the positive half cycle. So then we can first find the value of Vm across the capacitor, and then we use this value in the calculation. So it's important to understand that we choose that cycle which can help us to find the value of Vm across the capacitor, because if we have the value of Vm, then we can able to find the output voltage in the next cycle. So the selection of the cycle is very important. So that's why we select positive half cycle in case number 1, because with the help of positive half cycle in case number 1 we are able to find Vm, or we know that the capacitor is charged up to which value of Vm. We know that it is charged up to Vi, which is 10 volt in case number 1. So Vm is equal to 10 volt, as Vm is equal to Vi. Now find V output. Now find the output voltage. Now we apply KVL in figure number 2. The polarities at V out is shown in figure number 2. We apply KVL. According to figure number 2, there is a closed loop as shown in the figure. Now this closed loop is different from the closed loop which we discussed earlier in figure number 1, due to diode is now open circuiting. Now we apply KVL. So here the polarities of Vi is also different in this case. So we started with Vi, so it is positive Vi plus Vm plus V out is equal to 0. This is equation number 1. Now we solve the equation number 1. From equation number 1, V out is equal to minus Vi plus Vm. This is equation number 2. So we have already know from previous case that Vm is equal to Vi, already found from case number 1. So we put the value of Vm in equation number 2. Then V out is equal to minus 2Vm. Now calculate the value of the output voltage V out. So from figure number 3, Vm is equal to 10 volts, so Vout is equal to minus 20 volts. It means now the voltage is shifted downward because it is minus 20 volts, which is already, before it is already 10 volt is in the upward cycle, and the rest of the 10 volts are in the negative half cycle. But when you see in the output voltage Vout in the negative half cycle, all the DC level is shifted downward. So it means the total voltages are from 10 volt positive to minus 10 volt is 20 volts. Now this all 20 volt is now shifted in the negative half cycle in the downward direction, so it is minus 20 volt. Now in case number 1, Vout is equal to 0, and in case number 2 we found Vout is equal to minus 20 volts. This problem is solved now after finding the values of Vm across a capacitor and Vout through this clamper circuit. Now we can plot values of V input or V output voltages as shown in figure number 4. In figure number 4, the V output graph shows us that the total voltage V output is equal to 20 volts. Waveform is shifted in the downward direction as shown in the figure. Before it was 10 volt in the upward direction of positive half cycle, and the rest of the 10 volt was in the downward direction of negative half cycle, as in the previous slide in figure number 4 of the output waveform. But now it is totally shifted in downward direction of the negative half cycle without changing the shape of the waveform. In my first slide I discussed that it's the property of the clamper that the wave shape of the waveform remains unchanged, only there is a shifting in the DC levels either in the upward or in the downward direction. So this is the property of the clamper, that the voltage remains the same, and as we already discussed that the wave shape of the V output waveform remains the same as shown in the previous slide in figure number 4. Simply edit DC level either in the upward or in the downward direction, already shown in the figure number 4. The DC level is shifted in the downward direction in the previous slide. So in this second case, the total output voltage is shifted in negative half cycle. So it's a negative clamper and it's the property of the clamper circuits. So now the course learning objectives of this topic, clampers. There is an importance of DC levels in an AC sinusoidal signals. How to improve reinsert weak DC levels in any sinusoidal AC waveforms with the help of clamper circuits. These circuits also help us to shift required DC levels either in the positive or in negative cycles according to the design requirements. Students are now able to design clampers as per required DC levels in any AC signals. Students can differentiate between clipper and clamper circuits. Introduction of energy storing elements, capacitors in clamper circuits. And lastly, the applications of TV volume tuners act as a clampers. So all these are the course learning objectives of today's lectures, clampers.